Today we're going to go over a training that covers different boundary conditions for the steel structure we're going to have in place, and we're going to focus a little bit on different methods of application of these. Part of it will be this interaction that we have internally within the family of softwares in Midas between the structural software, that's Midas Gen, and our geotechnical software. We'll briefly cover that interaction, although it's not really the focus of the session. I'll show the model, but we do have a different training series that focuses more on the geotech point of view on how to create that whole setup. Today will be mostly on the building aspect of it, and in this Midas Gen, the structural engineering software, the boundary condition will be represented in these two cases as either a fixed boundary condition or a soil spring. And so these would be values that we'll be covering on how they can be calculated within the interaction with our geotech program, or how they can just be inputted directly in case you don't have that interaction. But there is just a bit of that clarification. This is a new feature that the programs have that we're about to launch our 2018 version of Midas Gen that will have this feature of interaction with the geotech software. The current version does have that capability as well with a patch that you can also download, and we'll briefly show that as well. But a lot of this will also just focus on overall the difference on what the results are by the boundary conditions and design features for this steel structure and the steel reinforced structure, all within the Midas Gen program. So quickly looking at the properties of the structure we have in place, as we see, we have steel sections, and we do have some of these columns that are steel reinforced concrete. So the steel is A36 and the concrete is grade C4000. So we'll go through this whole process, and like I mentioned in the end, we'll first use the optimal design feature of the program for the steel sections, and then we'll do the design of the concrete reinforcement for the steel reinforced concrete of the columns. Our starting file is actually a structure that we have as a basic tutorial that goes through all the steps on how to make this from scratch. So just to clarify that in this training, you will be, or I will be as a starting point already having the structure finished. In the tutorial that goes through these steps, which we've done in the past, and we can certainly include in the models for the people who want to try it on their own after the session. We'll include that PDF in that starting file, but they basically just fix the boundary in that model and just go through the analysis aspect of this steel structure. So we're kind of going to take it from there, where I'll be showing how to apply that boundary condition and then compare that to applying a different boundary condition, the soil springs, and finally just going through all the design features of the program. And so from here on out, I'll be switching back and forth between the PPT and the model. So this is Midas Gen 2017 version, and as I mentioned, we already have the starting file in place. A brief introduction to the interface. We have a series of, I guess our commands are in icon format, not a drop-down menu. And so you navigate through the software by going through these tabs in terms of what are commands, and they're kind of grouped together in a logical order. So you would first kind of set up how you're going to be either drawing the program or if you're going to be importing the CAD file. Then you would have some information about if you need to modify it, you could create grids for drawing, and then you would go through how to create what would be the elements and a few commands on either extruding or dividing. Then the properties and the materials would be here. If we give it a quick inspection, this is the basically the table that I had shown in the slides. These are the sections we're using. So as you see from the drawing, some of them are just steel sections, I-beams, and others are steel reinforced concrete. So these are the two materials that we're using. And then this will be kind of like one of the tabs we'll be working on, which is applying the boundary conditions. We'll be comparing fixed supports versus sole springs, spring supports. And then lastly, you would apply your loads, run the analysis, look at some results, which is what we'll be doing. And finally, we'll spend some time in the design tab, first designing the steel sections and then designing the steel reinforced concrete. So it can do it all in that respect. You can also kind of get an idea of everything you've made or the history of everything you've made, and very easy to modify here in the work stream. You can get some information about the structure, the number of stories, the number of elements, the sections. You can see that we have no boundary condition yet. We do have some beam and releases applied, and then you can see the loads that are, for this case, some static loads and some response spectrum loads. So just going through the steps in the tutorial, the first thing we're going to be doing is, let me get this out of the way, is applying a fixed boundary condition. So we would just go here to boundary. I'm going to change this view to either front or right view just so I can select the nodes more easily. So we have some of these ISO views over here. And I would go to supports, define supports, and I would just fix all degrees of freedom. Basically, I'm going to limit displacements and rotations and select what would be the base nodes. This last 7th degree of freedom is actually more for torsional, which I don't think we need in this case. So we can just fix rotations and displacement. And so when we apply it, what we see is these hexagons. And in this case, they're all in the same color, which means all of them have been activated. So it would just be, how we represent these. And so the first 3 are for displacements, and the second 3 are for rotation. So we're just fixing the nodes, the degrees of freedom of the base nodes. And we would just run the analysis. As I mentioned, we're starting off from a point in a different tutorial that goes through all the steps on how to create the structure, how to apply the loads. This training focuses a little bit on something different. So once you finish running the analysis, which in this case we see here from the message window, it took less than 2 seconds, we would go to the results tab to inspect the results. You see here they're all grouped together, and there's different, in this case we can take a look at, for instance, displacements, and you get these tabs. You can actually navigate from within these also here. You can go to the forces and then select some other kind of force if you wanted to see like the beam diagrams or stuff like that. And then here is where you would select your load combinations. Your sets of loads that you have applied would be the first ones, and then when you see the CBS, that's the load combinations that the program can create automatically for any kind of material, be it steel, concrete, or steel reinforced concrete. You can generate those by a design code. So in this case, we've generated these load combinations by the LRFD10. So we'll stick with the load case for self-weight, since the design procedure will be changing the dimensions of some of these sections and hence the weight, and we'll be able to see the changes in displacements and the changes in some of the force distributions strictly from the design process. So we'll stick with the load case for self-weight. And here you can select which direction you want to see. In this case, it's the displacement or deformations. And you can activate the legend if you want to see the structure deform. The default is to see it in exponential format. If you want to change that, you can go here to legend and do fixed and specify how many decimal points you want that to be. And you can always just change the units even after you run the analysis to something that makes it a little more clear. We do have different ways to see the structure. There is one of the icons here can change. For instance, if you want to see the section thickness, you can also ask it to show you or hide the connections. If you want to see node number information, you can do that. It makes it a little easier to see. So you have different options here in terms of some of the information being displayed. And the node numbers in this case will be important because that's how we can send information back and forth between the or within the programs in the Midas family. And so we'll be seeing some of these node numbers for the, I guess, the base come up in some of these tables we're going to be working with in a second. So you can activate and deactivate the node numbers here on display node. And like I said, this shrink option is for hiding the connection. And this is just to show or tick off the thickness of the sections. So we see here on the what would be results for the load case, we see displacements. We can go to the beam diagrams and take a look at, this would be Fx would be the axial forces. And then you can have like your moments or your shear forces. And they will all be bearing based on the load case. You can also get your reactions. In this case, we fix the base. So for instance, we want to see our vertical reactions. You could also see them here too. And so what we'll be doing from here would be to compare this under a different boundary condition, which would be the soil springs. Part of what I was mentioning that we can show in this interaction is that the 2017 version of this program with a patch allows you to export what would be the structure, which would be this MXT format, as well as the certain kind of results, which would be, in this case, we would be exporting reactions that will be then applied as a load in the Geotech program. And then from there, we could calculate, run the analysis in the Geotech, or the Geotech team can run the analysis with these reaction loads of the foundation and the soil in the other program and bring it back into table format to apply into soil springs. So we'll go through that in a second. I'll just first quickly cover that if you don't have that option, or regardless of how you get your soil spring information, you can directly just come here to spring supports, point spring, and we do also have the option for what would be rafts or piles. And you can apply directly the stiffness. This SDC would be like the K, the stiffness of your spring that you would be modeling the ground, and you can fix some degrees of freedom if you don't have all the information. For instance, here we'll just focus on the vertical stiffness. And you can apply those directly in this manner. So let's say we give it a stiffness of 15,000 kilonewtons per meter. And now we see we have a different color, even though the icon is the same. So these are soil spring representations instead of what would be just the fixed boundary. And so this is an oversimplification. We applied a uniform stiffness, but we would expect to see a different distribution than what would be if we just had the fixed boundary. Actually, in this case, I did not delete first the fixed boundaries. So this is running, we get the same result because it's running under the same previous condition. So now it's only the soil springs. Sorry about that quick confusion. We'll just run it again. It takes a sec. So under the same load case, now with soil springs instead of a fixed boundary, we see a much larger, in this case it's actually considered settlement as well, since it's not just the structure being deformed, but it's also sinking since we're modeling the soil as a spring. So we see this completely new distribution under soil spring conditions instead of what would be the fixed spring. But as we saw in the training, we're just giving it like a uniform value for the stiffness, which is not ideal. It could be, if you got the value from a table, if it's a very soft sand or clay, there are some simplification approximations that you could apply uniformly in some cases that might be more accurate than just, if it's a soft soil, then just fixing the base. But it's still not ideal. So the program does allow you to have this interaction. I'll quickly come back to the slides. Within the Midas family, like I said, if the 2017 version, there is a patch that you can create a text format of the building to be read by our geotech software. And you can also send what are nodal results. In this case, we would be able to export reactions in different directions, for instance, the vertical reactions, also into a text format. And this would be able to be imported into this is the GTSNX, this is a geotech software. And so you would be able to import the structure. And in this geotech software, you can model the soil as 3D elements with advanced theories, numerical theories for different kind of soil conditions. So if you have stiff rock or if you have a soft clay, all these different numerical theories, you can model them within the program. The reason we bring in the structure in this case is that the node information, the node number, will also be now connected to the raft in this case, so that when you import the reactions, they are automatically updated. And so then you're able to run the analysis without the structure in place, just what would be the traditional method of having the point loads. And then the geotech team can then from there extract what would be the new settlement under these more realistic boundary conditions of the soil into a table format where you can then calculate the stiffness, and you would be able to repeat this process for the different directions. In this case, we're doing it for the vertical direction, the settlement in DC. And this would be then sent back to the structural team. So sometimes this takes like a bit of an iteration between, especially if you're working with different platforms. The advantage, if you do happen to have a team that's working with within the family of programs of Midas, is that you can do this in a single step. And so just to briefly show you, this would be what the model looks like for the geotech team. And you can see these loads, static loads, were directly imported from just a text file. And then results from here would be just extracted and sent back. So this kind of interaction is some of the new features, as I mentioned, that will be available either by a patch in the current Gen version or available directly in the 2018 Midas Gen, which is coming out, I believe, this month. So going through this process, let's say however it is that your geotech team calculates the stiffness and sends them to the structural team, you would expect to see more of this kind of not uniform stiffness, but it's going to vary a bit from node to node on the base of the building. And so to be more accurate, what we need to do is to update our tables in Midas Gen. So you would get some sort of Excel file. This is where the node number becomes important. As we were looking earlier, it's at least for updating these kind of springs, it makes it much easier to keep track by node number instead of by coordinate system, since the table format in Gen is also it can be arranged by the node ID. And so it makes it much easier to just copy paste these values when you're updating these in the tables of Midas Gen if you have the node numbers also in order. So in the worksheet, I can go to here to those point springs that we first gave a uniform value. I'm going to change the units back to meters. And then right-click and go to tables. And so you see here that within the tables, the node numbers are also aligned. I mean, you can tell the program if you want to change the sorting, if you want it to be large to small or large or by maybe even other kind of parameter. And so here I can just copy paste from the keyboard to update these stiffnesses of the springs in the vertical direction and just rerun the model. What would be considered now a much more realistic condition than either fixing or giving it a uniform stiffness. And so when you run the analysis again, you would get, we'll take a look at the results for this new distribution. And so now we're seeing something that seems a little more reasonable. It's not going all the way to 90 millimeters. It's somewhere closer to 9, and it's not sinking on one side of the building. It's more actually looking more like just normal deformations. And so from here, you could also take a look at, as I was mentioning, the other results, like the beam diagrams for the forces. We do have some other options to take even a closer look. You can get a beam detail analysis by selecting a specific beam. So for instance here, or this column. So I'm going to hide the view and make it easier to select. Dun, dun, dun. Here. And you can get, well, beam diagrams and other more detailed results. So from here, what we would take is the, now we're going to go to the what would be the design aspect of the program. So you run the analysis, you have whatever boundary condition it is you want. I mean, you can do the design either way. And then you would create load combinations. These are the ones that are going to be used for the design. So we would create the load combinations for the steel. And we're also going to be doing design for the steel reinforced concrete. So we have to generate the load combinations for this as well. You can bring in your own load combinations from spreadsheet tables, import it, or you can auto-generate it by design codes. And so we have both the load combinations of the sections we're going to be doing. So we can now go what would be the design tab. We'll start off by going into the design of the steel sections. So we go here to steel design. We can first run a code check, the steel code check, and see if, there might be some sections that are fine, there might be some sections that are not, but we can get an idea of this by first running a check. And so we see here from this table that two of our members, our sections are fine, that we see here in blue that it says okay, and two are in red, which say not good. So we can click on, let's say this first section, we can get a more detailed result of what exactly is wrong with the section. So if you click on it, you would get this kind of report where you can see that basically what we're not passing are only some aspects to it regarding slenderness ratio and bending strength. And so these sections need to be redesigned based on these current, load conditions, load combinations. What we could do then is ask the program to do this directly. I'm gonna just go here to then tell it to go to steel optimal design. And we see it here going through all the steel members. And so we see first here, the same thing that we saw on the check is that 2 of the sections don't pass and 2 do. So we can just select everything and tell the program to design it. We can actually even give it information about iteration processes. So the program will go through, sometimes needs to go through several iterations. If, for instance, it changes, 2 of the sections, it has to recalculate the new distribution, and that might affect the third section. So it's sometimes good, even if there's no changes on program, will then let you know that after the second iteration, there's no need to go through a third, or there is no changes made about it. But you can be at least more sure than just running one iteration manually. You can just tell the program to go ahead and run 2 or 3, however many number of iterations in the process. So it's gone through its third iteration, and it's letting us know that the third time around there was no change between the second time and the third time. So this would have been fine just to run it 2 times. We see here now that all the sections are in blue. Everything basically has been redesigned, but now will comply with the GNOME, I guess the design code that we're using. So you can see the ones in sections 221 and sections 521 now have different dimensions. And so we can actually ask the program directly to give us a report about this, how these sections have changed, be it by weight ratio. Here, for instance, is one of these. Let me hide these other tables. So here we have, for instance, a table about the changes in weight of the different sections, the 4 steel sections we had through each iteration. So we see that, the 2 that were failing basically were the ones that had the biggest change. They both became bigger, hence more heavier, but only, after the third run, there was no change in that. So you can kind of get these reports for the steel sections and distributions to make it a little more clear on what's changed in case it's not exactly obvious when you're looking at the section options. The other nice feature of this is that you can specify, you can tell the program directly which sections to choose from. In this case, we're doing it from our database based on the code that we have. But if you have a particular limitation of what's available to you, or you only want to consider certain sections, you can specify a database of options, and the program will only go through the ones on that list. And so that would be how you can run what would be the optimal design for the steel sections. And of course, after it's done, you can just directly tell the program to go ahead and update the model with these new sections. And the program will run the analysis again once it's made those changes. So if we were to go back to the, we've been looking at results like the deformation, the settlement. We could go back one more time and take a look now with the new sections. They're heavier sections, they're bigger sections. And now the structure has a new distribution of deformation. It's now closer to 12 millimeters. So it's gone up a bit, which makes sense since some of our structure sections are now bigger, heavier. And you would also see a new distribution of axial forces, of moments and such. So you can make a report or have that as part of your report as you're going through the design process, is the new distribution of these. So that was for what was the steel sections. Now we want to repeat that process for what is the steel reinforced concrete. So we've already done the load combination, which is one of the prerequisites to run the design. So we go back to the design tab, and now we're in this column, which is the SRC. And so here the design code, we've already actually selected it when we ran the load combination. And so now you can just tell the program directly to do a code check. Although in this case, our steel section is, as we know, surrounded by concrete. It's reinforced. And this concrete actually also has rebar. So we need to specify before we run the check how we haven't said anything about it yet. So the program doesn't know. So we need to specify. I'm just going to select basically all the different columns we have. And I'm going to specify to the program the rebar distribution that I want. So I would tell him the number of rebars and which rebar to use. If you want to use a different, I guess, nomenclature for the rebar, you can actually change that by code. You can go here to Tools, Preferences, and you see here there are several tabs. There's one for Design, Load Code. And so here's where you can choose which code you're using for the rebar information, which materials to consider for the database of that. And so now if we go back, you see that the rebar is now given in by a different code. So what we'll do is tell the program that we have 8 rebars distributed in 4 rows, number 18. And the reinforcement has rebars of number 5 at 300 millimeters. And we can just apply it, basically activate this information. And so we see here now that the program now understands that there's the rebar in place so that when we run the design or at least the check in the beginning, it has all the information it needs. So we now go back and we tell it to do a column check. And we see for this case that 3 out of our 4 sections or column sections are fine, but this one in particular, what would be section 201, is not. So we can also take a same kind of report that we saw earlier for the steel section. We can get here a distribution of where the rebar is, dimensions of the sections, not just of the concrete, but also of the steel section. And we see what's really the issue in this case is the combined stresses, the compression plus bending. That's based on this equation, not passing. It's larger than what the norm requires. So this also needs to be redesigned. So it's a similar procedure for what we did for the steel section. We would go to then the optimal design. It's going to show us a similar table than what we did before. And we can directly select one of the columns. In this case, we can just select the column that we want. We don't have to do all of them. There are some options for you to specify the program if you wanted to consider only the axial forces or axial forces in the moment, and how the constraint is happening for the column splices, if it's internal or external. And here you can also do specify the number of iterations that you need. And you can go ahead and tell it to design. And so we see this section has changed. We can tell the program to update the section that we specifically designed in the model. And then we can go back to do another check. The only thing is we do have to retell, basically because there was a change to sections, this information was lost, so we need to reapply the rebar information before running another check. And so this time around, we go back and run another check with the new designed column. And we see now that everything is fine. And so you can get different kind of information. We've been looking at this graphic report, but you can also get other summaries or see ratios between them. We've been looking by sections, but you can actually even do by individual members, individual columns. So that would just be this change of view here. And you can get a small, this would be like a text report about the load combinations used for the section, design, dimensions, information. So going through these iterations, you can actually even estimate how much material and hence how much, I guess, money you could be potentially saving or the difference between the project. You can go here to tools and we have this option here called the bill of material report. So you can specify directly what you want to be considered in this. And so you can get, you can create these different reports maybe at the starting point and then at the end and be able to directly figure out how much material has changed. Well, I guess the units here, I should have changed it beforehand to back to kilometers. But you do get an idea, even by weight, of how much material is being, or the difference in material, in this case, how much material is being used for this structure. So some of these automatic features make it really handy to, in this case, we're doing it for only steel and steel reinforcement, but we can do the same for any material, which is another nice feature of the program, that you can also do it just for concrete. But that would basically be the conclusion of what is the design features that we have done. I will open now the, actually conclude this by showing, we can go back to the results one more time, and we would see a final change in settlement, although not too greatly after we design the columns. But what we would see is a higher axial force distribution in the columns after we design the steel reinforced concrete sections. So Midas Gen goes beyond just the building structures. It can be used for all kinds of, as I mentioned, materials. Within steel, the program is very popular for steel plants in various kinds of industries. And so you would see your same kind of diagrams as we've been looking for the structure, your moments, your shear forces, axial forces. This was part of a feature that I was showing earlier for the beam element. You can select a particular beam and get an even more detailed report of what would be the diagrams, be it the moment diagram or the shear force diagram or load distribution. Beyond what would be the steel plants, the program can also handle much more complex structures. For instance, the Beijing National Stadium was completely made out of steel and was also designed with Midas Gen, as well as some other, steel structures. There are, for instance, the Beijing airport or the Incheon airport in South Korea. Both are primarily supported by steel sections. And so this is also designed entirely within the Midas Gen program. So the structure, the size of the structure, the complexity of the structure, or even the type of material can all be handled under the same program. But now with the new feature and linking it to the Geotech software, it can give you even a more realistic approach based on the boundary conditions. So this is the conclusion of the training.